In the previous section, we developed the general framework of time-dependent perturbation theory. We showed how a weak time-dependent perturbation causes the coefficients of the unperturbed stationary states to evolve in time, and we connected those time-dependent amplitudes to transition amplitudes and transition probabilities. Now we move to one of the most important special cases in all of quantum mechanics, harmonic perturbation. This case is of central physical importance because many external excitations are harmonic in nature. The most familiar example is an electromagnetic wave. When a quantum system is driven by an oscillating field, the perturbation varies sinusoidally in time, and that simple time dependence leads to one of the most fundamental ideas in quantum mechanics, resonance. So this section is organized into 4 parts. First, we will study the formal setup of harmonic perturbation and derive the resonance condition. There we will see that a harmonic perturbation most strongly affects those states whose energy difference from the initial state is approximately equal to the driving quantum, which is h bar omega naught. Second, we will examine stimulated upward and downward transitions. In that part, the resonance condition will acquire a clear physical meaning. We will see that the perturbation can drive transitions both to higher energy states and to lower energy states, depending on the relevant resonance channel. Third, we will extend the discussion from a single final state to a dense set of final states. This is an essential step because in many real physical systems, the final states are not isolated discrete levels, but rather a group or continuum of nearby states. To handle that situation, we will introduce the density of final states and convert the sum over final states into an integral. Finally, in the 4th part, we will arrive at Fermi's golden rule. This is the central result of the section. It gives the transition rate from an initial state into a dense set of accessible final states under the action of a weak harmonic perturbation. Physically, it tells us that the transition rate is determined by 2 main ingredients: the strength of the coupling between the states, measured by the perturbation matrix element, and the number of available final states at the resonant energy, measured by the density of states. So the overall logic of this section is very clear. First, harmonic driving, then resonance, then transitions to individual and clustered final states, and finally, the transition rate formula known as Fermi's golden rule. This is a very important section because it connects the formal machinery of time-dependent perturbation theory to one of the most useful practical results in quantum mechanics. It provides the foundation for understanding optical absorption, emission, scattering, and many transition processes in atoms, molecules, solids, and semiconductor systems. Let's now set up the problem mathematically. We assume that the time-dependent perturbation has the harmonic form as shown. Each term consists of a spatial part and a time harmonic dependence. Here we use the plus and minus signs to distinguish the spatial parts corresponding to the 2 time dependence factors, e to the minus I omega 0t and e to the plus I omega 0t. So the perturbation is switched on at t equals 0. Before that instant, the system is completely unperturbed. Now let me explain why this form is both natural and important. We know that a physically measurable perturbation must be Hermitian, and a real oscillating field is written as the sum of 2 complex conjugate harmonic terms. That's why we do not keep only one exponential term such as e to the minus I omega 0t by itself. So in the present notation, you may think of these two terms as the two Hermitian conjugate components of a physically real oscillating perturbation. A very good example is the vector magnetic potential associated with a plane optical wave, as shown in this expression, where A sub e denotes the unit polarization vector of the plane wave, and K sub OP represents its wave vector. We'll see this expression again in the next chapter. Then, using Euler's formula, this expression can be rewritten as shown, which is exactly the same mathematical structure as the time harmonic perturbation written above. Here, the first term is the plane wave component with wave vector K sub OP, that is, the component propagating in the plus K sub OP direction, whereas the second term is the plane wave component propagating in the minus K sub OP direction. We see that one term oscillates as e to the minus I omega 0 t, and the other oscillates as e to the plus I omega 0 t. The spatial parts are also complex conjugates of one another. Together, they form a real physical field. So in the general expression for a harmonic perturbation, the subscript plus corresponds to the phase factor with a positive wave vector, whereas the subscript minus corresponds to the phase factor with a negative wave vector. Regarding the initial condition and perturbed wave function expansion in time harmonic perturbation, we assume that the electron is initially in the unperturbed state I. So the initial state is represented by the single unperturbed stationary wave function as shown. Now for times t larger than or equal to 0, the state of the electron is written as the general superposition of all unperturbed eigenstates, each multiplied by a time-dependent coefficient or amplitude a sub n of t. And as before, we use the perturbative expansion for a sub n of t up to the first order of the perturbation parameter lambda. Because the electron is initially in state I, the zeroth order initial conditions are given by these two expressions. So we have the zeroth order amplitude of state I be equal to 1 at time t equals 0, and the zeroth order amplitudes of the rest of the eigenstates are 0. So physically, the system starts entirely in the ith unperturbed state, and the harmonic perturbation then begins to transfer probability amplitude into other states. Let me emphasize the structure here. Nothing new is being assumed about the unperturbed basis itself. The only new ingredient is the time-dependent perturbation with a harmonic time dependence. That specific time dependence is what will ultimately produce resonant denominators and resonant transition probabilities. Now let's look at the zeroth order solution under this harmonic perturbation. Since the electron remains in state I initially, the zeroth order amplitudes are given by these two expressions. So we have the zeroth order amplitude of state I be equal to 1 for all time instants, and the zeroth order amplitudes of the rest of the unperturbed eigenstates must be 0. This is exactly what we expect. At zeroth order, the perturbation has not yet induced any transition, so the system simply remains in its initial unperturbed state. Notice that these coefficients are constant in time. That is consistent with what we already established in the general formalism of time-dependent perturbation theory. In the absence of the perturbative correction terms, the amplitudes in the unperturbed basis do not change with time. So at zeroth order, nothing happens except the stationary evolution of the initial state. This zeroth order result is very important because it tells us what to insert into the first order equation. Since only the ith zeroth order amplitude is non-zero, the first order coupled sum will collapse dramatically. That is what makes the harmonic perturbation problem analytically tractable. So the main message of this slide is straightforward. Before any first order correction is included, the electron stays entirely in its original state, which is state I, and all other zeroth order amplitudes remain zero. Now we move to the first order solution. From the general first order amplitude equation, we use the fact that the zeroth order amplitudes are given by these two equations, which means only the ith term in the sum survives, while the other terms on the right-hand side vanish. Therefore, the equation immediately simplifies to the one shown here, where omega sub mi is called the Bohr angular frequency between states I and m. This is the key first-order result for the present problem. Its physical meaning is very clear. The time rate of change of the first-order amplitude for state m is determined entirely by the perturbation matrix element h sub mi prime of t connecting the initial state I to state m, together with the oscillatory phase factor arising from the unperturbed energy difference. So once again, we see that transitions are controlled by the matrix element that couples the two states of interest. If the perturbation does not connect state I to state m, then the corresponding amplitude does not grow at first order. On the other hand, this slide is also where the resonance structure begins to emerge. The factor e to the I omega sub mit will soon combine with the harmonic time dependence of the perturbation itself, producing frequency combinations like omega sub mi plus minus omega naught. Those combinations are exactly what lead to resonant enhancement when the driving frequency omega naught matches the energy spacing between states. So this slide sets up the final simplification from a general coupled equation involving all states. We have reduced the problem to a single state initial condition and a much simpler first order differential equation. Now we substitute the harmonic perturbation into the first order amplitude equation. We obtain this expression, where the matrix elements are given by these two equations. They couple unperturbed state I to state m through the two spatial parts of a harmonic perturbation that form a Hermitian conjugate pair. As we will see later, the minus sign corresponds to the downward transition, whereas the plus sign corresponds to the upward transition. This is a very important result. The harmonic perturbation splits the dynamics into two oscillatory contributions. One contains the frequency combination omega sub mi plus omega naught, and the other contains omega sub mi minus omega naught. By integrating the equation shown here and applying the initial condition, we obtain this formula for a sub m1 of t, which is the first order correction term to the amplitude of the mth unperturbed state. It is the heart of the harmonic perturbation problem. It already tells us where resonance will come from. If one of the denominators becomes small, the corresponding amplitude becomes large compared with the non-resonant contribution. So the resonance behavior arises when either of the denominator is close to zero. Now let's interpret the integrated first-order amplitude physically. The result we just obtained is repeated here. We can now see that the amplitude becomes especially large when one of the denominators is close to 0. That means the perturbation is most effective when omega naught is close to plus minus the Bohr angular frequency or the transition frequency, omega sub mi. Now, since omega sub mi is expressed in terms of the energy difference between the two unperturbed states involving in the transition, this resonance condition can be further written as shown in this equation, which is the central resonance relation. It tells us that the harmonic perturbation most strongly affects those states whose energy difference from the initial state is approximately equal to the quantum energy h bar omega naught carried by the oscillating time harmonic perturbation. Physically, the plus sign corresponds to moving to a higher energy state, while the minus sign corresponds to moving to a lower energy state. In many practical cases, especially when the system is initially in a lower energy state and the field frequency is near resonance, the term with omega sub mi minus omega naught is the dominant one. The other term is then far from resonance and contributes much less strongly. So the main message of this slide is very simple but very important. A harmonic perturbation most strongly excites those states whose energy spacing matches the driving quantum h bar omega naught. This is the essence of resonance in time-dependent quantum perturbation theory, and it is exactly the result that prepares us for the next topic, deriving transition probability under time harmonic perturbation and ultimately Fermi's golden rule.